we are going to start talking about flux. And this is something, just like Gaussian surfaces, that we're going to need to talk about for a few sections before you really see the full context of why we are talking about it. So initially we're going to talk a little bit about an analogy for flux, and this is airflow. So flux is a kind of a general thing that can exist in physics in a couple of different ways. So we really might talk about the flux of air through a loop, which has to do with the flow of air. But something I want to keep reiterating is that when we're talking about electric flux, we are talking about field lines, field vectors, but the field itself isn't moving. So that's one thing that's a little bit misleading, is that in many cases when we think about flux, literally something's moving. For electric fields, that's not the case. So airflow. Imagine that I have a room, and in my room there's, some sort of fan or something. That's probably what a fan looks like. So the fan is spinning, and that's pushing the air this way. And so we have a little loop, say, made out of wire, and we're asking just how is the air flowing through that wire? So if the wire is oriented as it's shown here, so kind of perpendicularly, all of the air is passing through. And again, this is fundamentally a three-dimensional problem. So if you were looking completely edge on to the loop, you would see all of the air flowing to the right. So this is going to be our maximum flow. Like if you orient the loop in a different way, maybe less air would flow through, but that's what we're going to think about now, is what happens as we change our angle. So we could, for instance, turn the loop on its side, and now none of the air is actually flowing through it. It's flowing above and below it, but not actually passing through. So this is, again, thinking about motion in this case, but for electric field, we're just thinking about vector direction. And one of the things that's helpful here is to think about your normal vector. So the normal vector, this n hat guy, is perpendicular to the surface. So when the normal vector is aligned with the airflow, you have maximum flux, so maximum air passing through. When it's perpendicular, you actually have no air flowing through the loop. Now, in both cases, air is flowing, and in both cases, we have the same loop. So we see that the orientation is really what matters here, and so that angle is going to be something that comes up. Now, we could actually pick some random angle, and this is when it starts to get very tricky to represent this as a three-dimensional problem, but instead of our loop being vertical, where it was max, or horizontal, where it was 0, we now can pick some angle where it's in between. Now, in this case, the angle we're looking at here is between the airflow, right, this direction, and the normal. And so we're looking at this angle, theta. So here, in the maximum case, we actually would have said that theta equals 0, and in the minimum, the 0 case, we would have said that theta equals 90 degrees. So in this case, once we say we have an arbitrary angle, there's two different ways we can actually think about it. One, we can project and say that if it's at an angle, there's kind of just one side that's perpendicular to the airflow. So instead of having the entire length of the loop, you now just have projected it. Another way to look at it, which is what this figure is showing, is that you can, and notice that I've actually, these two things are not meant to be the same. I was just trying to communicate some arbitrary angle here. That in this case, we have the projection of that velocity vector of the air onto the normal vector. So that's what's going on here. So we have some component of the velocity that is perpendicular to the loop, and so that's the part of the velocity going through it. So there's two different projections going on here, and so you can think about it actually either, and we're about to talk about how the area comes in. You can either think about projecting the area or projecting the velocity vector. In both cases, you get a cosine theta, as long as you've defined theta to be this way, where it is the angle that the velocity vector makes with the normal direction. So again, this is just all meant to be an analogy. Suddenly, we're going to have electric fields appear. So now, nothing is actually moving, but we have an electric field vector direction, and then we have the normal vector of our surface. And in this case, it's not, the loop would kind of surround the surface, so now we're talking about a surface like a piece of paper or something. So there's two ways to define it. So, or kind of three if you follow my reasoning from before. So one is we just project the electric field vector to be perpendicular to the surface, which means aligning with the normal vector. So this accepts that there's going to be some electric field that is not pointed kind of at the surface, and so we only look at the component that is in fact perpendicular to the surface. So in that case, E perpendicular becomes E cos theta. Now, as I mentioned before, another way to think about this in the airflow case is to just ask, is to project kind of the side of this. That makes a little less sense when nothing's actually moving. So that is one reason to prefer projecting the electric field vector onto the normal vector. So the definition of flux in this case is that, so again, this key equation here, that flux, which is capital phi, so phi, you might be familiar with writing it that way, you might do a little lowercase. This is capital phi. And to make it distinct by hand, you might draw the little things, the little top and bottom bits. And so this is electric flux. Sub E just means electric. And the reason we would write that is because later we're going to have magnetic flux. So it's helpful to be in the habit of writing E so that you know you're talking about electric flux, since later that can be different. And so we have the electric field strength, and we have the area of our surface, and then cosine theta. Note that this is assuming that the strength of the electric field is the same everywhere over our surface, which we will soon be discussing what happens if that is not true. So, notice here I had EA cos theta, and E is clearly a vector. Now, maybe this looks like a dot product to you, and that's because it is. But to have a dot product, you need to have two vectors. And if you haven't seen something like this before, but you really understand vectors, your first thought might be, hey, this can't be a dot product because area is a scalar, it's not a vector. But we can make it into a vector. And how we do that is we say that the direction of the area vector is simply your normal vector. And now, yay, we have a dot product, and we have two vectors. And so in general, the dot product of any two vectors, and let me try to come up with some other letters given that A is already chilling out here. So let's say that I have the dot product of M vector with N vector. Well, that is literally equal to the magnitude of M vector times the magnitude of N vector cosine the angle between them. So if you look, that is all we've done, is that the flux is going to be the dot product between the electric field vector and area, assuming that our electric field vector is constant over the surface we're talking about, and that would be constant in both magnitude and direction. Okay, so our area vector is always perpendicular to the surface, and again, that's just like our normal vector. So it's perpendicular to the surface. That can be a little bit tricky. The magnitude of it, so the magnitude is simply the area of the surface, which is just the scalar area that you're used to talking about. So anytime you see a vector, that's what it means. This is again a case where you want to be really clear in your notation, and if you're just talking about scalar area, don't put the little vector symbol on it. If you mean area vector, put the vector symbol on it. So again, that has meaning. Right now, we are not going to worry because you might notice that, hey, it could also be down. Isn't that also perpendicular to the surface? But notice that that vector and that vector are not the same. They point in opposite directions. For now, don't worry about this. We're going to be talking about closed surfaces soon, and then we can distinguish between the two of these. Right now, this is ambiguous, but by the time we get to using this, it isn't going to matter.